Okay, so we are introducing a big topic right now. This is going to go on for some time. The topic is trees. And we are beginning with the conception of rooted trees. So first, a general definition of a tree. So what is a tree? Tree is a set of nodes and edges that connect them. So in other words, the main criteria here for it to be tree is that there is exactly one path from, or not from, exactly one path between two nodes. So let's define a path. So what is a path? Path is a connected sequence of edges. So if I draw some random does it look like a tree to you? It is a tree based on what? Based on this, that exactly one path. You take any two nodes, there is exactly one path going from one node to another. So that makes it a tree. So then what is a rooted tree? So rooted tree is one distinguished node is called the root. So if I pick here, I will pick this node. I will designate this to be the root. So now typically nobody draws a tree like this. It's hard to see a tree like this, right? So I would draw, so let's number them. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the trees are usually not drawn like this. The trees are drawn, you put the root above and you take the children out. So 1 and 4 are the children of the root node. 1 has got 2 children further. You've got 2, you've got 3. 4 has got 3 children. There is 5, there is 9, and then there is 6. 6 has got 2 children, which is 7, and it is 8. This looks like much like a tree. But definition wise, nobody is stopping you to draw a tree like this, because all it needs is that exactly one path exists between two nodes. And there is a designated node called root. Okay, so every node, let's say n, except the root node, has one parent p. Okay, so take any node, say 9. 9 has only one parent, which is 4. Take 6, only one parent, which is 4. But take the root, it does not have any parent. So therefore, accept the root. So what is the definition of a parent? So parent is the, so what is a parent? The first node on the path from n to the root node. So how do I know that 4 is the parent of 6? So from 6, if we walk up to the root, the first node that you encounter is 4, and therefore 4 is the parent. And therefore, based on that, n is considered to be P's child. And that is why it is better to draw a tree like this. You can easily see the parent-child relationship compared to drawing a tree like this. Okay, so the root has no parent, and a node can have any number of children. So I can have all of a sudden this node number 6 have, let's say, 100 children. That's also is possible. There's nothing stopping it from doing that if it's just a tree, a rooted tree. Okay. So more definitions. These terminologies are important for us to get familiarized with, because they will be used quite conventionally when we are talking about a problem, talking about a solution, so on and so forth. So leaf is a node with no children. So what is a leaf here? Well, can someone call out? Can you tell me one leaf here in this tree? Which node does not have any children?
2.
Yep. Then siblings. So siblings are nodes with the same parent. So here, what would be the nodes that are considered to be siblings?
2, 3.
Exactly, very good. Then ancestors. So ancestors of a node n are the nodes on the path from n to the root, including n itself and the root. And if A is an ancestor of n, then n is a descendant of A. Okay, so in this picture, can you tell me what is going to be an ancestor? What would be all the ancestors of 8, let's say? Who can list down all the ancestors of 8?
8, 6, 4 root.
Very good. So it inclusive of the node itself and the root. Very good. Okay, what is the length of a path? Now, please pay attention here. So length of a path is number of edges, not nodes, number of edges on the path. Okay. And so node to itself, in that case, the path length would be equal to 0, right? So number of edges on the path. So for example, if you pick the root node and 9, what would be the length of the path? Root node and 9.
2.
Yes. So you just count the number of edges. Okay. Okay. Then depth. The two more very important concept to remember, because we don't want any confusion in terminology. So there is depth and there is height. There is length, depth, and height. Okay. So depth of node n is going to be what? It is the length of the path from n to the root, not to the leaf, to the root. And depth of the root node is equal to 0. Okay, and height of a node, height of node n is going to be equal to length of path from n to its deepest descendant, and therefore the height of a leaf node is going to be 0. So when you're looking here, so let's be pictorially, if you have to depict. So when we are looking at the height of 4, right, it generally measured from the leaf node. So this is the height. So what would be the height of 4 here in this case?
2.
Exactly. So the deepest node is not 9, it is somewhere here, 7, 8, 100, and all these things. And the depth of 4, we look from the root. So it is only 1. So d is equal to 1 and height is equal to 2 for the node 4. Okay. So we can say that height of a tree is equal to height of what? So if I have to know what is the height of the whole tree, what should be the height of?
Height of the root.
Exactly. So you want to measure this to the deepest descendant, right? So that's going to be the height of the tree. So height of the tree is equal to height of the root node. Okay. Subtree rooted at n is a tree formed by n and its descendants. Okay, let's look at here. So what would be the subtree rooted at 1? So the subtree rooted at 1 would be this guy. So this would be a subtree rooted at 1. So you have to take that and then take all the descendants of that. Now let's define a very, very special tree and very, very commonly occurring tree, and that is a binary tree. So binary tree is a tree where no node no node has greater than two children. Okay, or to say it positively, less than equal to two children. Okay, and every child in a binary tree is either the left or the right child. Importantly, even if it is the only child. So binary tree would look like something like this. So suppose it's the root. Note here, this is a child, single child of this parent. This is also a single child of this parent. But this one is a right child, this one is a left child. And therefore, every child is either a left or a right child in a binary tree. Okay. All right. So now let's talk about the representation of a tree. So representation, let's talk about just of a tree first, so of rooted trees. So as you saw, for rooted trees, the children can be of can be any number, and as a result of which, you cannot just put a data structure like children of certain size or an upper bound. Then, if you have a node having 100 children and another node having one child, then you are paying an overhead for wasting 99 slots. And therefore, a common way to represent rooted trees is to first represent the item, whatever the type of that item is. You can optionally represent the parent and the siblings are directly forming a linked list. So directly linked. That's a typical way you represent the rooted tree. So in other words, this would look like something like this. So class tree node. And here the item can be of any kind. So let's say some object type item, and then you have tree node star representing the parent. Then you have tree node representing the first child, and the tree node. So these are the two together forming sort of linked chain. So next sibling. So these are forming the linked chain. So you can think of, if you're drawing a number of nodes, so this is the root. And so in this case, you can see so for this node, suppose I'm trying to track. So let me draw a few more nodes. It becomes more interesting. Okay. So for this node, suppose how the representation would look like is that, so it has got an item inside. It has got a parent pointer. And then this has got a pointer to the first child. So this is the first child pointer. And then it has got a pointer to the next sibling. And likewise, this will have the pointer to the next sibling. Is the representation clear? So parent, first child, and then each of these are carrying the next sibling pointers.
So
Well,
for the next sibling this is pointing to, it wouldn't carry a pointer to the parent, or it would still?
this one will also carry its pointer to the parent.
Thank you.
Okay. Maybe I might be confusing you by writing this one here. Yeah, so here, what I wanted to draw is that with respect to this node, right? If you just look at this node, this has got a parent pointer, this is the first child pointer, and then pointer to the next siblings are built up from here. So this is forming a linked chain. That's the key point. But this kind of connection is valid for every single node. Okay. So this is considered to be the most efficient representation when you are having any number of children. Okay. Now, of course, this is the definition of a tree node, right? So if you have to define what is going to be the tree itself, so let's say this is the rooted tree, then you have to designate, so tree node star root, right? You need to have a designated root, and that's going to be the class structure for the rooted tree. Okay. Any question, any other doubt based on what we discussed so far? All right. So maybe I will not discuss anything else in the rooted tree. We'll discuss the traversal next week. But I would like to leave you with one C++ thing that I wanted to introduce you. I just wanted to give you a simple way of interacting with the files, and just wanted to give you a standard way of doing it. So let me just